So IE, right? I know it's a bit of mess. I'm going to copy this diagram again. Let me see if I paste what happened. Okay. Undo. Hold on. I'm going to paste. Yeah. It's too crowded in the other diagram. So the shear flow, okay, for this case is look like this. Let me draw it properly. Let me draw it off, so it's short. Then it got longer, longest, and then it got shorter. And again, over here, the up and the down, these are the terminals. Okay, and the last rule, which we have written down, which I've highlighted to you before, the thickness geometry is perpendicular to the shear flow. Okay, so over here, i.e., this distance, the shear flow is going down that way. This distance is your T. So over here, right, when we are deriving this expression over here, our thickness, okay, so while deriving our thickness is equal to B, right? You can see our thickness is equal to B. So now what we're going to do next is we're going to assemble the whole equation together. Okay, we're going to assemble a whole equation together. Let me paste the diagram. So we have shear xy is equal to Vy divided by 2/3. Right? Our second moment area is 2/3 BC squared, or BC cubed, sorry. Then our first moment of area is B/2. We have B/2 multiplied by what? B/2 multiplied C squared minus by Y squared. And then over here, we have our thickness. Our thickness is equal to what? We just derived our thickness is equal to B. Okay. Our thickness is equal to B. Okay. So what we are going to do now is I'm going to progressively get rid of some terms. Okay. So what we have is B and B can cancel. Okay, we can cancel. And then the next thing we are going to do is we're going to substitute the area is equal to what? The area, the cross-sectional, substitute the cross-sectional area which is, I'm going to call it A, is equal to 2BC, right? Because the top is C, the bottom is C, so it's 2C multiplied by 2, multiplied by B is 2BC. So the shear XY now is equal to Vy. Now we will have this as our half, right? Then we have C squared minus Y squared. So now we are going to split our 2BC, right? And then we are going to have our C squared, and then the whole thing divided by 3, right? So this will be equal to Vy right? I'm going to bring the 3 to the top, multiply by 3 over 2, right? C squared minus y squared. Then I'm going to have the denominator. And we know this term over here, 2bc is going to your a. Okay, so this is going to be the a. And then we have c squared. And then finally, this will be equal to 3 over 2, right? We have Vy over A. And now what I'm going to do is I'm going to introduce a C squared inside. And then finally, we have derived that 3 over 2 Vy over A multiplied by 1 minus by y squared over C squared. Okay. So with this, right, the derivation is not that complex at all. Now we can look at it. It's pretty straightforward. So when we have derived this, right? So if we were to now look at this profile now, right? And then if we were to declare this line over here, right? So this is our shear XY. And then we have our this is our Y, right? So what we come up with is this expression over here. And this basically, these lines is basically shear XY is equal to Vy or 3 over 2 Vy over A, right? 1 minus by y squared over c squared. And we know at this point, our shear XY max is equal to 3 over 2 Vy over A. Right? Why is that? Because this term over here, right, at the maximum, y is equal to what? 0, right? Because over here, we know that the datum is at the centroid. Okay, so that's all the deriving, and we cannot. The deriving is important because later on, when we do the analysis, okay, we have to follow the rules, which is from the derivation of the math. Okay, so the rules cannot be broken. Okay, so now I'm going to start by getting you to warm up, okay, about the first moment of area. Okay, why the first moment of area is critical. Okay, now if we look at the expression, in general, there's only two formulas for this shear flow. Okay, is shear XY is equal to Vy over Izz Qz over T. Okay, or you can find the shear flow is equal to Vy over Izz multiplied by Qz. The problem is always the what? What is the first moment of area? Okay, where is the first moment of area and what is the first moment of area? Okay, so now we are going to look at a cross section. Okay, we're going to look at a cross section. This is the cross section that we're going to focus on. Okay, we are going to focus on the cross section. So the question comes to this: what is the first moment of area at point A? Okay, and the next question is, what is the first moment of area at point B? Okay, I repeat again, we are going to determine what is the first moment of area at point A, and we're also going to determine what is the first moment of point B. Okay. Okay. So we are going to we're going to do this exercise. Okay. So we are going to look at determine the first moment of area for points A and for point B. Okay. So before we start, okay, we have to determine let me draw our transformation first. This is our Y, this is our Z, and then we have our rotation about X. Okay. So we have to determine the geometric, and we are going to declare that we have a Vy coming down. Okay, we have a Vy coming down. So we're going to determine the geometric centroid. Okay. Of the structure. Why the geometric centroid is important? Because the geometric centroid is the what? Is the datum. If you don't know where the datum is, you're as good as game over. Right? Okay. So we are going to take our reference at the top first. Okay. So I want you to get used to this term over here. All right. So this is our flange. Okay. This is our left web. And over here, this is our right web. Okay. So section. So we know that Vy, we are going to look at ZZ. So we declare that this is our width. And we declare that this is our depth. Okay. So section, so we have our flange, left web, right web. And then we also still do our width and depth. Okay. So the width is 160. The depth is 20. So this is equal to 160 times 20. So 3200. Our left web, the width is 20. The depth is 80. Okay, so 20 times 80 is equal to 1600. The same, 20 times 80, 1600. The Y bar, from top, right? So this is equal to 20 divided by 2, which is equal to 10. And then the left web will be equal to 20 plus by 80 divided by 2. So 20 plus by 80 divided by 2 is 60. So it's the same, 20 plus by 80 divided by 2, 60, because the data is from the top. And then we do the W, T, and small y bar. So 320 times 10 is equal to 32 times 10 to the power 3. Okay. 320 times 10 again, right? 1600 times by 60 is equal to 96 times 10 to the power 3. Okay, and it's also equal to 96 times 10 to the power 3.